Training a neural network is like hiking down a mountain in thick fog. You can't see the bottom. All you can feel is the slope right under your feet. In this video, we'll uncover the 4 ideas that turn that blind hike into learning: backpropagation, gradient descent, the learning rate, and the optimizer. Together, they let a network teach itself, and they do it up to 10 million times faster than the obvious approach. First, the mountain itself. Every weight inside a network is a knob we can turn. Pick a setting for all of them, and the network makes predictions with some amount of error. That error is called the loss. Now imagine plotting the loss for every possible setting of the weights. You get a vast landscape of hills and valleys. High ground means a bad network. The lowest valley is the best one we can find. Training is simply the search for that valley. The catch: the network is standing in fog. It cannot see the whole map. It can only feel the slope beneath its feet. To take one reading, the network does a forward pass. It takes an input, say the pixels of an image, and pushes those numbers through its layers. Each layer multiplies, adds, and reshapes the numbers, then passes them on to the next. By the time the signal reaches the far side, the network has produced a prediction. That is its current best guess. Next, we check the guess against the right answer. The loss function measures the gap between them and boils it down to a single number. A big number means the prediction was badly wrong. A small number means it was close. This one number is our altitude on the mountain. To learn, the network has to bring it down. But which way is down? That is what the gradient tells us. For every single weight, the gradient answers one question. If I nudge this weight up a little, does the loss go up or down, and how steeply? Collect those answers for all the weights, and you get the slope of the landscape at your exact position. The negative gradient points in the direction of steepest descent. That is the way downhill. Now the star of the show: how do we actually compute that slope? This is backpropagation. After the forward pass, we know the loss. Backprop sends that error signal backward through the network, one layer at a time. At each step, it asks how much this layer contributed to the error and hands the blame back to the layer before it. Layer by layer, the error flows in reverse until every weight knows exactly how it affected the loss. And here is the secret: backpropagation is nothing more than the chain rule from calculus. Each operation in the network has a simple local derivative. How its output changes when its input changes. To find how a weight deep in the network affects the final loss, you just multiply the local derivatives along the path connecting them. Backprop is that multiplication, carried out efficiently for every weight at once. You almost never write this by hand. Modern frameworks do it for you with a tool called Autograd, short for automatic differentiation. As the forward pass runs, the framework quietly records every operation onto a tape, a computational graph, and remembers each step's local derivative. To get the gradients, it simply replays that tape backward, multiplying as it goes. Because every intermediate value is stored and reused exactly once, computing all the gradients costs about the same as a single forward pass. That reuse is why backprop is millions of times faster than working out each derivative from scratch. Armed with the gradient, we finally take a step. This is gradient descent. The rule is beautifully simple. Take each weight and move it a little bit in the downhill direction. New weight equals old weight minus the step size times the gradient. Do this once and the loss drops a tiny bit. Do it again and again, thousands of times. Step by step, the network walks down the mountain and the error shrinks. That step size has a name: the learning rate, and it matters enormously. Make it too small and training crawls, taking forever and sometimes getting stuck on a ledge. Make it too large and the network leaps right over the valley, overshooting back and forth or flying off the mountain entirely as the loss explodes. The art is finding a learning rate that is just right, big enough to make progress, small enough to settle into the valley. Backprop gives us the slope and gradient descent takes the step. But there are smarter ways to step than always marching straight downhill. The recipe that decides how to use the gradient is called the optimizer. Plain stochastic gradient descent, SGD, just follows the slope. Momentum remembers the direction it has been heading and builds up speed, so it can roll straight through small bumps and narrow ravines. Atom goes further, giving every weight its own adaptive learning rate, tuned from the recent history of its gradients. Drop all 3 on the same landscape and you can watch their personalities. Plain SGD zigzags down a narrow valley, bouncing between the walls. Momentum carries through, smoothing out the path. Atom adapts on the fly and often reaches the bottom first. Same mountain, same gradients from backprop, very different journeys. So which optimizer should you use? There is no single winner. Adam is fast and forgiving, and it is the default for most large language models. But on many vision tasks, a well-tuned SGD with momentum actually generalizes better, reaching a lower error on data it has never seen. The optimizer is a genuine choice, and it changes how well your network ends up learning. So let's bring the four together. Backpropagation tells you the slope of the mountain, the gradient. Gradient descent takes a step downhill. The learning rate decides how big that step is, and the optimizer is your strategy for stepping. Four ideas, one single journey down the lost landscape, repeated until the network finds its valley. That is how every neural network learns. Thanks for watching.